Good afternoon. I want to commend the conference organizers for this fantastic venue and the lunch and all the arrangements, including the documentation of the proceedings. Excellent job. Okay. I'll be very brief on the introduction about BrightSource, as many of you are already familiar, as Jason said, with the company and the projects. Obviously, we are focused here today talking about solar thermal for electricity application, but we are very optimistic about the future for solar thermal in other market applications, including hybridization, industrial steam, and desalinization. Similar to what Solar Reserve said, we are very much a technology company that provides core technology and services, conceptual plant design, solar field design, solar field control systems, receiver conceptual design, commissioning and startup is arranged. We have headquarters in marketing and operational offices around the world. Our shareholders are some of the largest players in the industry, including GE. And likewise, we are privileged to be partners with Shanghai Electric in our joint venture here in China. But what I want to focus on before I get into the lessons learned is really to talk about the experience of BrightSource over the last several decades. The core technology engineering of our team designed and built these SEGs, solar energy generating systems, in California, going back almost 30 years, all of which are still now in operation and performing above 100%. So they're very familiar with solar trough technology. In 2008, we constructed a demonstration and research facility, which we still operate today. In fact, it's a 6 megawatt thermal, and it was used to validate the models and the software as part of the Department of Energy Loan Guarantee Program. For Chevron, we designed, built, and operated for 3 years an enhanced oil recovery project in California to displace the use of natural gas. That was Chevron's interest. Low natural gas prices, Chevron's not moving forward today, but nonetheless, technology was important to demonstrate and operation conditions, and again, it probably performed at about 106 to 180% of design. Ivanpah, of course, came online in 2013. We are now in our 3rd year of commercial operation. That is 3 towers with a total megawatt output of net 377 megawatts. In 2015, we began operating a molten salt receiver, which we are now using for our projects that we would be constructing with our partners in South Africa. In 2017, we expect to become commercial at the Ashalim project, and that project represents all of our next generation technology, including wireless control, self-powered heliostats, and I'll be speaking about that in detail tomorrow, so I hope you have an opportunity to come and hear that. And we are certainly hopeful here that with our partner Shanghai Electric, that we'll be constructing a project in China that uses BrightSource's technology as well as Chinese technology under the pilot program. So, let's focus on lessons learned. To understand what our experience has been, it would be helpful to recognize what roles BrightSource played in the development of Ivanpah. We were the original developer, and at financial close, NRG Energy became the majority shareholder and operator with an investment of $300 million. But for the project, we supplied the solar field, the heliostats, components and control systems, the methods and tools. I'll talk about that more. The assembly and solar field construction was done by Bechtel, the EPC contractor. The solar receiver steam generator was provided by Riley with coatings, proprietary coatings developed by BrightSource. Siemens was the turbine supplier, and Bechtel managed the other equipment and installations. Now, one of the things I wanted to say about how did we get this right. This project was built on time and on budget in a period of 33 months. The assembly equipment was producing, and you see here, 500 heliostats a day. But one of the keys to reducing costs and ensuring a successful project was the use of Six Sigma meaning something virtually free of defects, 99.999% free of defects. We used it to address design, procurement, and construction challenges, and we targeted 5 areas: material handling, heliostat assembly, field transportation, solar field installation, and power tower erection. And in each area, the team found new and more efficient ways that drove greater performance and better results. We used modeling tools to make sure all the materials came in and out without hiccups or interruptions, including how the heliostat containers were moved throughout the site. With the data from the models and feedback from traffic and logistics, the team redesigned the area to allow for stacking of heliostat containers. Choosing specialized yard equipment meant that containers could be moved more easily in the smaller space provided. Here you see the inside of the heliostat assembly building. Given that there were 3 towers, it made sense to assemble them on site and serve that, although we'll talk tomorrow about how that has changed. It was a very popular place with the workers because it was the only place that was air conditioned in the desert. So if you were lucky to work in the heliostat factory, you remained quite cool and comfortable. It's not uncommon to find it's not uncommon to find an assembly line in a manufacturing facility, but here we are. It was a state-of-the-art facility. It featured robotics, specially designed to lift the mirrors and to stack them in the pads, where the pads are placed on the back of mirrors. The team used mock-up assembly testing facility to conduct time and motion studies. And the results of these studies enabled us to redesign the building to efficiencies that would enable them to produce 500 heliostats per day, or 1.7 heliostats per minute. It also led us to separate the building into 2 distinct areas, one smaller building for the bonding and pre-assembly, and then the larger building that you see here. Moving the heliostats out into the field, there were 173,500 heliostats to be installed. 500 of them had to be transported each day for 2 years. Based on the size of the project, this was roughly equivalent to 35,000 miles of travel. I should have done the kilometers, I'll have that for you tomorrow. 35,000 miles of travel to move the heliostats. And we analyzed various transportation models that uncover the most efficient routes to ensure that the team had a transportation system that allowed for enough crane, tractor, and trailer combinations to sustain the installation rate. Once the team figured out the best way to transport the materials and assemble the heliostats, they needed to evaluate the field installation, and this process involved analyzing how holes, where we inserted the pylons into the ground, and finally the heliostat installation. We do not use foundations because we've developed technologies to allow for the insertion of the pylons, the support beams, that hold the heliostats to be put into the ground. And there are many benefits we'll talk about later. But the efficiencies that we created in the heliostat and solar field installation process enabled the workers to exceed the 500 heliostat a day goal. And at the peak of construction, they were installing a rate of between 600 and 750 heliostats per day. In fact, an interesting point is from the time of start of construction to the time of commercial operation, that averaged 1 heliostat installed per minute. Here you can see an image of a crew installing. We believe there are significant advantages to the type and size of heliostat we have here because they represent a balance between optical efficiency, cost, and maintenance, because you do need to access the control modules. The success of this team really depended upon input from the workers we had. They gave us invaluable feedback on workflow, cycle times, equipment functionality, challenges associated with pylon installation, but by being part of the process, the workers became more invested in the success of the project and the desire to continuously improve the process. We would have competitions to see which teams could install the most pylons or build and install the most heliostats per day, of course, according to project specifications. These competitions created a tremendous sense of team spirit and pride in the work, And it was that drive to continuous improvement that carried over into the work of the other crafts, and they were invested in the project, they showed their pride, they put forth the extra effort, which continued through project completion. If you look in the back, you'll see the tower. That was another first-of-its-kind challenge, was to lift that 339-foot steel tower and 3 2,200-ton boilers. And so it was built in parts, lifting the boiler in pieces, and we created multiple assemblies and as much construction on the ground. We're using different techniques for the next project. The lower project of the tower on the foundation, and the upper tower pre-assembled on the ground and lifted into place. So as I mentioned already, we reached the goal, and they averaged 1 per minute during construction time. Environmentally responsible. I want to highlight that the project itself also uses air cooling. We heard that earlier today. Air cooling is virtually less than what's called 100 acre-feet water, enough to supply 300 households in a year. Very little. And we're adjacent to a golf course where we use a fraction. But it is a 95% reduction from traditional wet cooling technologies. If you look carefully at the picture, you'll see the natural contours of the land were maintained. Not only did this save money and protected the environment, but when the rains came, and it does rain in the desert, we found that maintaining the natural contours of the land allowed the water to move through. In fact, when we were 3 months into construction, and we had a 70-year flood event, water came rushing down. Those heliostats are designed to withstand 3 feet of reduction, almost a meter, over 30 years, and still maintain their structural rigidity and integrity. Air quality, we're concerned with species protection and plants. I could spend hours or days talking about all the requirements, but we're proud of the work that we did there, and you can see a desert tortoise way off on the left. So from an operation and maintenance perspective, BrightSource provides a continuing services agreement. We provide software upgrades. We provided and designed the initial mirror washing equipment, and the energy as managing partner for operations and maintenance. And obviously, we include the respective warranties from us as a supplier into the project. Regarding performance, we have a dedicated team that focuses on continuous improvements. They look at data collected constantly, and we identify data, the cause, action, and the forecast against what the model was expected to do compared to what the actual was on any given day. And that information is organized into startup and shutdown, maintenance, weather, operations, solar field, balance of plant equipment to identify and continuously improve that performance. On average today, we are regularly exceeding the capacity of about 105% of the rated capacity. And from an energy production perspective, we regularly exceed 109% of the projected energy on sunny days. So if you look at data, there's a lot of projects under the DOE Loan Guarantee Program, and you see different patterns based on the location. They're not all, so you'll have different weather data, you'll have different performance. But looking only at monthly data doesn't give you a true picture, because the performance guarantees are really based on annual performance. And so here we are, and this chart shows the 12-month trailing production, which is to say each bar represents an entire 12 months of production. And as we move from left to right, we drop off 1 month, we add 1 month. So we smooth out the variations between the months. And what you'll see is we have an obligation to PG&E to deliver 70% by the end of year 2. And although we were close on a 1-year basis, clearly the trends, we've begun to surpass that already on a regular basis. But I would make a point here regarding the pilot, and that's true for all these projects. From experience, we can tell you, you need time to figure out how to work the details or work the plan to get it begin to optimize. And that can take 1 to 2 years. It's not unusual. But we feel very confident, not just in this project, but in all the previous projects, that we are on schedule and on track to deliver 100% as was expected. I would also add that much like Solar Reserve, all of these startup times were factored into the financial documents and the power purchase agreements and the regulatory filings. So this was expected from the beginning. We're in line with those expectations, and we're pleased with the progress. So looking forward, some final thoughts about CSP with thermal energy storage, because that clearly is the future. There's a lot of benefit, and I would encourage anyone interested, this report, which was put together by the Concentrating Solar Power Alliance, is available for download. It's also in English and in Chinese. And it describes the calculation methodologies, the benefits of synchronous generators, thermal inertia, all of the things you would expect with a traditional power plant in detail, and it includes an assessment of international projects. I highlight this because having just come from a day-long presentation, a day-long meeting in Washington, D.C. with the Department of Energy looking out over the next 20 years, it's clear people are beginning to focus not just here in China and in the U.S., but globally on the value of flexible resources, because it is a substitute for traditional fossil-fired generation like a natural gas plant. One of the things people were predicting, now this is to show California, and it's looking at, over time, how does the load shape change from the perspective of the grid operator as you add more variable resources like wind and PV to the grid, in this case, as you add more photovoltaics. And several things happen. The peak load, the net load, which is the demand less the must-take resources the grid operator has to have on the solar, is changing and is becoming less. It's also shifting later in the day. In fact, the issue becomes, as you have a lot more PV approaching 10% on the grid, that your peak demand is now occurring when the sun's down. Which means that as you add more PV, the capacity value begins to approach zero. And therein lies the dilemma. We certainly want to encourage more PV and more wind. And so the value of CSP is not that it competes on a cost basis with PV, but the flexibility and the value it delivers enables greater penetrations of PV, wind, and other variable resources onto the grid in order to maintain reliability standards at a reasonable cost. So these were the predictions of net loads shifting, steeper ramps, and energy displacement. And many of you have seen this slide. If not, it's in this report. Output variability impacting grids. So here again is the net load. And I only draw your attention here because instead of expecting the load dip to be in 2014, when 2014 happened, it came 3 years earlier. And so you can see that when they were expecting, in 2017, they actually hit 3 years early the 2014 reduction, creating all these other conditions. So there are many solutions, including scheduling, demand response, but CSP with storage is an excellent one and provides what the grid operator is looking for. And here's the prediction, as we already see this past spring, where we had excess generation in California as a result of solar PV on the grid. So I say this because these issues are growing in importance. We hear them in all the markets that we operate. In many cases, countries that don't have transparent wholesale markets will look to set aside a target for CSP with storage, which is what China has done, which is what Morocco has done, which is what other countries are doing, because it does provide that important benefit. So I'll leave you with that, and I'm happy to take any questions, but we feel very positive here about the value of CSP with storage, and look forward to working with our China partners and customers. Thank you.
下面我们也有2个问题的提问机会，请大家踊跃提问。
Yes, sir.
Okay, thank you for accessing this presentation. It's my honor to have opportunity to ask a question. Regarding to your presentation, as you mentioned, you have the water-saving solutions. One is use the air cooling condenser, and the other thing is you make good use of the rain to clean the mirrors. But do you have the other ways to clean your mirrors? Because other ways, you can't guarantee your cleanness of the mirrors. If you can't guarantee your cleanness of the mirrors, you can't guarantee your output from the power plant.
Actually, you can, and I'll explain how. Because when you build the solar receiver in the tower, the solar field is larger than what you're going to require throughout most of the day. In other words, we don't require all the heliostats to be focused onto the receiver all hours of the day. There's excess capacity. So in the same way you can compensate for cloud cover, which is changing, you can also compensate for dust accumulation, because we actually monitor in real time the accumulation and specular reflectivity of the heliostats in the field in a dedicated area with cameras that feed back into us. So at all times we know not just what the we always know what the reflectivity is, and we can make a determination as to when it's appropriate to then go out and clean. One of the things we found is that we expected to have to clean 6 to 8 times a year, when in fact, by using more mirrors, even though they might have a slightly reduced reflectivity, we can compensate for that over time, thereby reducing maintenance costs, and sometimes we only need to clean 4 times a year. We are also aided by the occasional rain, which is nature's way of cleaning mirrors, and we don't have to pay for that, so we're happy for the rain, but not happy we didn't produce power that day. But that's how we monitor in real time, and we can control, and we know at all times what the obligation is to the customer under the contract, and that's part of the software and solar field monitoring capabilities.
Thank you for your answer, but I have one more question.
Sure.
As you mentioned, you are cleaning for 6 or 8 times per year. But if you can't have the rain in time, just like if you didn't have the rain for 1 or 2 months, and the mirrors are still dirty, how can you clean it? As you mentioned, you have the machine, or you are all used by the labor to clean your mirrors.
I'm sorry, I didn't understand the question.
So is used a machine to clean your mirrors, or you by hand, or just by the labor? You hire the people from the local?
Yeah, we actually clean both ways. The reason that originally there was more robots and automation at Ivanpah was due to the high cost of labor. But you'll find in other markets where you go in South Africa, and we actually clean manually with an outside crew for the heliostats that are further away from the tower. When we're close to the tower, we can control where they stand, so we'll create rows that will line themselves up, and we have a machine that goes down. It's very efficient. But as you get further away into the solar field, the distance between heliostats is greater, and the contour of the land changes. And so we find that tomorrow you'll see how we create those ring roads and access roads. I'll show you tomorrow in my presentation. But that allows a crew to go in and then to very quickly clean manually. The one thing I would encourage for us as we talk about in the future where are the cost reduction opportunities is thinking about alternative mirror technologies with hard surfaces that may not require cleaning with water. In other words, abrasion-free, different coatings are possible that they've been looking at now for some time. That also would withstand pitting that can become a problem. In other parts of the world, like Australia, the challenge in the morning is not cleaning, they have dew. And depending on the night temperatures, that can cause a delay in being able to ramp up. So what I would say is that we always optimize for a given site location. And that's true of the heliostat design, the maintenance methodologies, taking into account the attenuation in the air, the expected dust or wind levels or wind loading, but we look to optimize, and again, tomorrow we'll go into much more detail about the solar field design and optimization.
Okay, thank you.
现在再给其他人一个提问机会。
你好，我是中国太阳能跟踪器产业链。我有一个问题，就是说，中国现在也大张旗鼓做光热的这些建设啊，因为我们的地理环境跟这个跟美国跟西班牙都不一样，就是说，您觉得我们在建设在中国建设这样光热电站的话， 从成本上，从各个方面，这个转换率方面，可能这个都效率方面都可能会，低于这个国外的一些电站。您有什么建议在这方面？我们怎么样能够缩小这种差距？另外一个问题就是说，现在就是说，这个光伏电站现在是非常经济啊，也就是占比很大，在整个的这个新能源发电当中。那么光热的话，这个CSP 很小的比例。您觉得未来他们会不会有一批，就是说，您觉得大概要多长时间，我们的光热能够追上光伏？谢谢。
Can someone translate? I didn't get it. There was no translation. Sorry. Could you repeat that? Just kidding.
因为这个问题过长，可能很多朋友没有听清楚。请刚才那位先生再简单重复一下第一个问题，不要问2个问题了。第一个问题。
第一个问题，因为我们呢，虽然中国的电价呢没有起来，但是非常的热络啊，这个电站也是大张旗鼓都在建。但是我们的自然条件，包括日照，包括温差，风沙，然后这个就比较恶劣了，就是像比在美国加州啊，这个条件呢就差很多。那我们在建设成本方面，这个发电效率方面，都可能不如在美国啊或者西班牙这样的一个效果。那我们的成本啊都可能会高的话，您认为我们有些什么建议能让我们尽量的缩少跟国外这个电站的这样的一个水准吧，造价之类的，谢谢。
So Joe, I'm going to help you translate. The question is, China's solar resources is a little different from the U.S. And given these constraints, what measures do you think could help alleviate the pressure on the construction as well as the cost of the project?
That's an excellent question. I'm probably not the best person to answer that because I'm not in design. But what I would say is the approach that we take in each project is very careful research, not just into the atmospheric conditions like how much DNI, what's the weather variability, but we look carefully at the soil conditions. Because so much of what is, we talked about pylon insertion without understanding, without foundations, requires a clear understanding of the type of soil conditions, what the rainfall conditions, and so coming back to recognizing the lower amount of DNI, part of the answer is we have to find ways of delivering the energy faster and cheaper. Reducing costs means reducing the amount of construction time. It means projects that are less risky, so we're able to borrow at a lower interest rate. It's a combination of many, many factors so that it can appear in different markets to be economically attractive. But maybe a better way to think about that is the concept of a reference plant design, which is to say we have a standard by which we expect we can produce and operate a power plant for a given labor rate with a given amount of DNI at a given interest rate or borrowing cost. And then we make adjustments to that in our model based on the specifics of the particular location and make decisions around what type of material costs are either above average or below average for supply, given the physical location, shipping costs, and logistics. So all of that, we have a reference design, and then we make those adjustments, and it's those adjustments that allow us to say, if it's 1.1, we'll find a way to deliver the project with storage and operate it successfully over time. But I also say it's clearly our expectation that that's not where we stop. The industry as a whole has to continue to drive down costs through everything from new materials, volume, learning experience, new techniques, lower interest, lower financing. All of those have to contribute in order for us to stay competitive with the alternatives to grid reliability, and that can be PV plus batteries, it can be natural gas, where you have natural gas, but where there is a focus on carbon-free production of energy and we remain competitive, we find that CSP with storage complements, and it's that focus on value that we have. So I hope that answers your question, but I'm happy to speak further after here and put you in touch with our technical team.
那么十分感谢焦子先生的一个精彩分享和对问题的一个回答。